One of the primary reasons why we factor things is because we can solve equations with them. And very often it's the easiest way to solve equations when you factor them. So this relies on this one concept called a zero product principle. And what this says is that if we have two numbers that are multiplied together that equal 0, that one of those numbers or expressions or whatever a and b is, one of them has to be 0. There's no other way to get that. Now, if you had addition, of course, there's many ways to get that. If it's a plus b equals 0, then a can be 2, b is negative 2. A could be 5, b could be negative 5. And that, so when you're adding, there's many different ways to do it. But the only way you can arrive at a 0 through multiplying is that one of the factors is 0. So if we factor polynomials, then we'll get to the point where we can actually solve them. So, for example, here's an equation that doesn't necessarily represent any particular form or anything like that. We just have terms kind of spread all over the place. So you can attempt to solve it, but really the most straightforward and the complete way to solve it is by rewriting everything so you have a 0 on one side. And so here I'm rewriting this just by bringing the 5x squared and the 2x to the left side. And so I have this polynomial equal to 0. And now the question is, does this factor? Well, the first thing we notice is that we can factor out an x. Now it's important not to divide both sides by x because we'll eliminate the x then. And we don't want to eliminate it because x equals 0 is part of the solution to this. And that would go away if we just divided both sides by x. So we factor it out. And then we have this 3x squared minus 5x minus 2, and we factor that by grouping. So the way I do that is I say, okay, 3 times negative 2 is negative 6, and aha, negative 5 is 1 off of negative 6, so I know I'm taking the difference, so I can say negative 6 plus 1 equals negative 5. And that gives me my numbers that I can expand to do factoring by grouping. So I have this 3x squared minus 6x plus x minus 2. And so if I pair them off, and instead of parentheses, I'm going to put them in brackets, you can see I can factor out a 3x from the first two terms, and I can just leave that x minus 2 alone, and put parentheses around it, so that has an implied 1 in front. And now I can factor out that x minus 2 group. And by doing that, I'll get my factors. Okay, so this is fully factored. And I have 3 factors now that any one of them can be 0, and I have a solution to my equation. So if I just look at them in turn, I have, when x equals 0, then regardless of what the other two terms say, the first term, that x is 0, so everything becomes 0. So that's a solution. The next one, and I realize I probably did this one too briefly, when does 3x plus 1 equal 0? Well, if we solve for x, we get x is negative 1/3. And so x can be negative 1/3, or x can be 2. Now, one of the things that is tempting to think about is that x can be all 3 of those values, and that the 0 goes in the first x, the 1/3 goes into the next x, and the 2 goes into the next x. That's not true at all. X can only be one value through that equation. We have 3 solutions to this equation. That means that if all the x's are 0, or all the x's are negative 1/3, or all the x's are 2, then you have the solution. Okay, so let's take that x equals 2 as the case. So if we have the first term is going, when x equals 2, that first term is 2. The second one is going to be 3 times 2 plus 1, so that's 6 plus 1 is 7. And then the last one is going to be 2 minus 2 is 0. And so this is true. I have 14 times 0 is 0. 0 equals 0. So the other two terms evaluate to some value. It's not important what, because that one value that makes this a solution, where x equals 2, turns out to be the one that really dominates the behavior of those terms, because it just makes everything 0. Okay, any questions on this? Did you follow how I did the factoring by grouping? Was that okay? Okay, so I know you had some of these yesterday and you were to turn them in today as homework, but let's just kind of put a bow on this by doing this last one, okay? Give that one a try, and I'll ask one of you to come to the board and solve it at the board. Okay, anybody want to put this on the board? I know a couple of you have finished. Targa, did you get it? Why don't you come up? Great, terrific. Everybody follow what he did there? So, moved everything to one side, and then he factored it, and then found that those factors are 0 when x equals 5 or x equals 3. And so just a couple points. When I see people, doing this, sometimes they'll stop writing the equals 0 here because, they factor it and things like that. You'll get to the right answer, but I suppose, but it's not really complete. Like it's done perfectly well here, where everything is, done very orderly, and you got, both answers. The fact that he put a comma between the two, or I wrote the two out, doesn't really matter. Both indicates that it indicates that we have two solutions. One equals -5, and 1 equals 3. So if you look at my chart, I have forgotten my 5, or my negative there. So let me make that a -5, like that. Okay? All right. So that's it. Melissa, you had a question on that. The ordinary use of the word rational, is not what's meant here. Usually you think of when a person's rational, they're reasonable, and when they're irrational, they're crazy. That's not the use of that word here. Here, the word rational comes from the word ratio on the inside. And so when we have a rational expression, we're talking about an expression that contains a ratio. Same thing with functions. If we have two polynomial functions, and we take the ratio of them to make another polynomial function, or another function, we call that a rational function. So what will be different about these is that we have to worry about the domain a little bit, because we have a ratio, we have some division. It's possible that the denominator get to be 0, and when it's 0, we end up with an undefined expression or a function that's undefined at that value. And so we'll call, we have to be careful then about specifying a domain, because we do want this thing to equal some type of a number or a value of sorts. And so we have to be careful, never set that denominator to be 0. And for the most part, that might be implied that it can't be 0. So, how are you? Everybody up on this one? Okay, I'll wait a minute. Okay. So let's find the domain of this function. This is these two functions, actually. We have 4 over x minus 3. Now that will give us a value of whatever we like. We can put in whatever x we like, except x equals 3. Because if we put in x equals 3, we get 4 divided by 0, right? And so when we talk about the domain of this function, we have to say it's all real numbers except 3. And so we can write that a couple of ways. We can just write x does not equal 3. And when we're just stating the function, attaching that to the function will be good. Or if we want to really fully specify the domain, we can write it in set builder notation, and we get this x such that x does not equal 3. Now on the second one here, we know that the domain has to restrict us from values of x that'll make that denominator 0. In other words, x squared minus 9 can't be 0. That's what we want. So what we do is we actually figure out, okay, where does it equal 0? And so I'm actually solving this equation for x squared minus 9 equals 0, and I find that x equals 3 or x equals negative 3. That just tells me where x squared minus 9 equals 0. But we don't want that. So what we do is we will write our domain restriction as x does not equal 3 or x does not equal negative 3. So it's really important to understand the context of how you're using these symbols. The equal sign I'm using here because the question is here, where does this equal 0? And so I'm going to find out where it equals 0, and then I'm going to turn around and say, okay, I don't want it to equal 0, so I can't let it be these values. Now, it's an easy thing to fall into when you're writing a lot of these things, especially when you're doing mixed type problems, that when you solve an equation like this, that all of a sudden you're writing x does not equal negative 5 or 3, and that's not what you mean. You mean that to be the solution. So this is written properly. This is when you want x to be equal to 0. But when you want that denominator not to be 0, then you write it as a not equal sign. So be careful about the symbols that you use here, because it may say something very different than what you really want it to. Okay, so we can write this in set builder notation just by putting the notation that says the set of x such that x does not equal 3 or x does not equal negative 3. Okay, so let's go on to simplifying rational expressions. So if we have, let's say, u, v, and w, and these u, v, and w can be anything, numbers, variables, polynomials, algebraic expressions, that when we say uw over vw equals u over v, in other words, we're canceling out the w, that's only valid when v does not equal 0 and when w does not equal 0. So I'll put that in the form of just an example here. If I have this expression here where I have 8x cubed plus 4x squared over 20x, to simplify that, what I want to do is I want to factor it as to the fullest extent that I can. And then I notice there's an x in common, that x squared and that x, one of those x's will drop out. And the 4 over 20 will make that a 5 in the denominator. So when we cancel everything out, we get this x times 2x plus 1 over 5. But we're not finished here. What we have to do is look at, we're trying to simplify this expression. So we want exactly the same results from this one that we get when we simplify it. And what we are missing here is that we've missed now the domain restriction that says that x can't be 0. In this one, it's very clear that x can't be 0 because when x is 0, you're dividing by 0. So we call that an implied domain restriction. Here, we have to actually state the domain restriction, and so we'll call this an explicit domain restriction. So we have to say this because this is only equal to this first, to what I started with when x doesn't equal 0. They're the same in all other values, but we have to say on the second one that x can't be 0, even though 0 evaluates to a perfectly good number here. We say 0 times 2, 0 plus 1, that's going to be 0 over 5. 0 is a perfectly good number, but the fact of the matter is this expression does not equal 0 when x equals 0. The value of this expression has to be undefined because we had that original domain restriction.
So every time you have 0 over a number, it's going to be undefined?
No, 0 over a number is perfectly good. That's a 0.
Yeah.
A number over 0 is undefined.
Okay.
Okay? And that's an important distinction because you don't want to just throw zeros out. This equals 0. This is undefined. Okay, so let's talk a little bit more about domains. So we have this number, or we have this rational expression, x squared plus 2x plus 1 over x plus 1. When we just have that, it's implied that x can't be negative 1, right? Because when you try putting in a negative 1, you have, you end up actually, in this case, of 0 over 0, which is not defined. Okay, so if we simplify it, if we say, okay, let's factor that numerator, and we get the denominator, and that thing then cancels the x plus 1, and we get x plus 1, we lose the implied x cannot equal negative 1, so you have to state it explicitly now. All right, so when I'm writing this, if my original function is this, an equivalent way to state that function would be x plus 1 when x does not equal negative 1. So those two, for every value, are exactly the same now, because the first one, you could put in any number and get a number except negative 1. That's when you get 0 over 0. And on the second one, you're stating by writing the domain restriction right behind it, you're stating that x cannot equal negative 1. So we go from implicit, on this side, this is an implicit domain restriction. This is the explicit domain restriction.
Picking it back real quick.
Yeah. Okay. Okay, let's go over a couple of examples again. I want to simplify this expression. So my approach in simplifying is I'm going to look in the numerator and say, oh, that it has a common x, so I'm going to factor that out. The denominator factors pretty readily at x minus 4 and x plus 2. Now I haven't fully factored the numerator yet. But one of the things that, factoring it partially like this, doing the easy stuff, like just factoring out the x and then factoring out the one that's easier, it'll give you hints as to how this factors. Now, x squared minus 16, you see, is the difference between two squares. So that would factor as x minus 4 times x plus 4. And so then we can notice that the x minus 4 is in common in both the numerator and the denominator. So that can factor out. We can cancel that out, and we get x over, or x times x plus 4 over x plus 2. X cannot equal 4. All right? So when you get to this point of making this simplification after everything's canceled, go back up to the version that you have that's fully factored and look at the denominator there, and you say, which ones are implied correctly and which ones do I have to state? So the x plus 2 is retained in the final answer, so we don't have to write x cannot equal negative 2 because that's implied, but we do have to take care of this and say that in this expression x cannot equal 4. Even though when you plug in a 4, you get 4 times 4 plus 4 is 4 times 8. It's 32 over 6, so you get, a perfectly reasonable number, but that's not what this expression simplifies to. We have to retain the fact that we have this domain restriction because of this x minus 4. Now, probably a little bit more precise mathematical way to think about this is that when we're dropping out the x minus 4 over x minus 4, we can cancel that because that equals 1. Right? We're just factoring out a 1. That's all we're doing. Well, it only equals 1 when x does not equal 4. If x equals 4, we have 0 over 0, which basically doesn't work. And so this principle of canceling out these factors only works when we're canceling out something to get to a 1. And we're not getting to a 1. We're getting to a 0 over 0 if we assume that x can now equal 4. It can't. And that's why we retain the domain restriction there. Okay, so here's one for you. Actually, 2 for you. Or maybe it's just 1. There's 1. Okay, so that's essentially what I did. With the factoring, I did my factoring by grouping again. First I factored out the negative in the bottom to make inside the parentheses, polynomial in standard form with a positive coefficient for the leading term. And then I know that 2 times 4 equals 8, 8 plus 1 equals 9, so I'm going to factor by grouping that top one. And I get exactly the same factors here. And so I'm going to reconstruct my problem using those factors and do the cancellation and note the domain restriction. Okay? Yes?
Would you also, besides x is not equal to 4, do you still write x is not equal to -3?
You may, and I'm not going to mark it wrong, but it's not necessary because this already implies that x can't be -3. So in other words, if you're going to use this expression now in whatever you're doing and you're going to plug in numbers, it'll stop you when you try and plug in a -3 because you'll end up with division by 0. Okay, so that's sufficient. But if I go ahead and plug in a 4 here, it doesn't work. So, or I'll get a number, but I don't want a number. I want it to be undefined there. So that's why I write the domain restrictions. So the ones that are required are the ones that go from being implicit to being being such that you have to name it explicitly. Certainly if you list x cannot equal -3, that's not wrong. It's just not necessary. Okay, now most of what we've done in this class has been doing problems that involve a single variable, and occasionally you come across where you have more than one variable if you're working with like a scientific formula or something of that sort. So the basic process is the same, but occasionally your domain restrictions will look a little different the way you notate these. So if we go through and do the initial factoring, and the first thing I'm going to do is look for a common factor in both of them. So I'm going to, a common monomial factor, so I'm going to notice that there's a 2 in each of the terms in the numerator, and there's a 5x that I can take out of the terms in the denominator. I end up with this thing. And now I have to factor both the numerator and the denominator a little further. That x squared minus y squared, that's the difference between two squares, so that one's easy. That goes to x minus y times x plus y. But that one on the top is perhaps a little bit more difficult because it has the y in there. So when you have something of this form, where you have the highest term of x here, and it may have a numerical coefficient or may not, but this middle term just has an xy, and then this last term has a y squared. Try factoring it as though the y didn't exist. And then in the second term, that linear term, just add the y back in, and you'll get your answer. So if I were to factor that way, I would have ended up with x minus 1 times x plus 2. And so I'm going to add the y in there to account for this y squared in the back, and then just the way my terms add up when I'm expanding that by foiling, I'm going to get a single y in the middle expression here. So sometimes just ignoring that extra variable will help, but you should check it. If you do it that way, put it together and see if it foils out for you. See if it really expands properly. Okay, here we notice we have the x minus y in common, and so my answer is going to be 2 times the remaining terms, 2x plus 2y over 5x times x plus y. But what I took out was this x minus y, and so I don't want that to be equal to 0. And if that can't be equal to 0, all that means is that x cannot equal y. And so then the way you would write the answer to this thing is just write the expression with x cannot equal y. And that retains the proper domain restriction by stating it explicitly. So your domain restrictions aren't necessarily x equals a number, x equals 3 or x equals -5 or something like that. It can be an expression that is in x or y. Okay? Okay, time for you to try one. Actually, try 2. So then the key with finding these domain restrictions is just make an equation, make it equal to 0, find out some expression that causes it to be 0, and then write it exactly the opposite, where it does not equal 0. So in this case, y does not equal -8x.
So does it matter if you solve for x or y?
No, you can write this anyway. That can be -y does not equal 8x, or it could be -1/8 y equals x, or does not equal x. Just some relationship there, okay? There's no real requirement. It's a good question, though, but there's no form to it.
I don't know the domain part.
You're close.
Is it -2?
Yep, that's it. Okay, so what did she do? She factored out the 3 from the numerator, and then the denominator factored into 2 factors of m plus 2n. And then you had the difference of squares, which could factor, and then 2 of them cancel. And so you get this expression. Now, she put the correct domain restriction there and I didn't. Okay, why don't I need to put a domain restriction explicitly there? It's already implicit. I guess the strict way to say that would be, it's already implicated. That sounds like a crime, doesn't it? Yeah, so, you see, we had two factors of this m plus 2n. One of them remains, and so this is fine. There's nothing wrong with putting it, you know, and so you don't even have to look for this kind of thing if you don't want to. But it's not strictly necessary because you already have it implied there.